engineers utilized a system design approach for the modeling of the MicroAlgae biofuel production facility using SuperPro Designer, a software that is currently used by a large number of companies on the commercial market today. In biomass production, algae is cultivated to a high density and stress under nutrient deprivation to overexpress acylglycerol lipids that are used to create our biodiesel molecules. In harvesting extraction, the algae cells are concentrated to a high percentage and are lysed so we can get at the intracellular product of interest. In lipid extraction, that product of interest is separated from the biomass and cell debris, and in transesterification through a series of reactions, those molecules are made into fatty acid methyl esters, also known as biodiesel. The first step in microalgae biodiesel production is the cultivation. Cultivation accounts for over 40% of the cost in microalgae production and is an area of intense research on making this technology commercially viable. Our engineer, Miranda, Mientus, designed our cultivation system in a two-step hybrid method utilizing both photobioreactors and raceway commons. In the photobioreactor, as pictured above, microalgae species Nanochloropsis, which was chosen for its high lipid productivity, its well-characterization, and its scale of potential, is grown in the photobioreactor to high cell densities. Nutrient deprivation is a process by which microalgae are cultivated under nutrient limitations in order to overexpress certain compounds such as pigments and lipids. In our raceway pond, as pictured above, the algae are stressed under nitrogen deprivation to overproduce our acylglycerol and increase the total amount of lipid content within our cells. Next, I'm going to pass it on to Miranda, and she's going to discuss the pretreatment, harvesting, extraction, and transesterification of subsystems.
So, as you can see, our subsystem is our pretreatment and harvesting. To explain harvesting is basically where we're going to concentrate our algae cells to try and remove some of that volume so we can decrease our later downstream costs. And then in pretreatment, what we're trying to do is break open our algae cells so that we can more easily access the lipids within them. So we decided to use a three-step system for this. We're first going to flocculate and filtrate our algae to harvest it, and then we're going to send it through a pulse electric field in order to pre-treat it. So starting on the left, with our algae cells from cultivation, we're going to mix it with a flocculant and send it to an IP clarifier. As you can see from the picture, that's what a clarifier tank would look like in liquid. And so what's going to happen in this tank is the algae cells are going to clump together and they're going to settle to the bottom of the tank. And when this happens, we're going to more easily be able to remove water and therefore concentrate them. Then these clumped algae cells are going to be sent to a filter, an example is shown here. And in this filter, again, we're going to remove more water to be able to further concentrate these cells. Then, finally, when we have our concentrated algae stream, it'll be sent to a unit operation that can perform a pulse electric field. Now, pulse electric field is similar to electroporation, where we're going to send an electric current through our algae biomass. And in doing so, as we know, electroporation opens the pores of algae cells. And the pulse electric field is similar. However, it is a little more aggressive, so it's going to make those algae cells burst and therefore release its contents. And then these lysed algae cells are going to be sent to the extraction subsystem. So back to our full system, we're going to talk about the blue one now, which is our extraction. So we decided to utilize an extraction method called supercritical carbon dioxide extraction. So there are three steps to this. First, we're going to gather our carbon dioxide and compress it and heat it up to supercritical fluid conditions. And then we're going to send it to an extraction tank where we can perform the actual supercritical carbon dioxide extraction. And then we're going to send it to a different unit operation to remove our carbon dioxide, so we're just left with our lipid stream. So starting on the right this time, we're going to start with our lysed cells from harvesting and send it to our extraction tank. And then we're also going to bring in our carbon dioxide. We use both a recycled source and an input source. And in our extraction tank, going to mix our carbon dioxide fluid and our algae biomass fluid. And because, well, from the picture, you can see the lipid is going to be the little orange dot, and then the white dots surrounding it are the carbon dioxide. So basically, when we mix the two fluids, the carbon dioxide is going to surround our lipid molecules. So when these two phases, the carbon dioxide fluid and the water, are able to separate, the carbon dioxide is going to bring the lipids with it, and the rest of the biomass and waste that we don't need are going to stay with the water. This will make the water easy to remove, and so we're just left with our carbon dioxide fluid, which we can send to our flash tank. And in the flash tank, the carbon dioxide can be removed by reducing the pressure, and we'll just be left with our lipid or aquaglycerol stream, which can be sent to our transesterification subsystem. So now we're going to switch to diesel production instead of just oil. So in diesel production, as you can see, it's pretty complicated. There's a lot going on. So we split it into 4 different sections. First, we're going to send it through a decapping step. Then we're going to remove the fatty acids. Then we're going to send it through the transesterification reaction. And finally, there will be a purification step. So, starting on the top left, we'll start with our alpha-glycerols for extraction, and they'll be sent to degumming. So in degumming, our lipids are going to be reacted, or phospholipids are going to react with citric acid. And in doing so, the citric acid is going to cleave the fatty acid and a hydrogen phosphate from these phospholipids. And in doing so, when we mix our lipid stream with water, the water will be able to dissolve the phosphates and remove it when we centrifuge the stream. Then the leftover lipids are going to be sent to our fatty acid removal. And in fatty acid removal, the fatty acids need to be removed because they're going to slow down the transesterification reaction later. And because we obviously want this to be as efficient and fast as possible to produce as much biofuel as possible, we want to make it more efficient to remove these impurities. So we added NaOH, and in doing so, NaOH is going to cause the fatty acids to clump and form soaps. So because these clumps are going to be much denser than the typical lipid and nitroglycerol, we'll be able to centrifuge it and remove them from the stream. So then finally, we're just left with sent to the transesterification subsystem. And in transesterification, this is our main reaction that is going to be producing our biodiesel. So basically what happens is the main lipid, our alpha-glycerol, is going to react with methanol. And doing this, these two molecules are going to create fatty acid methyl esters, or biodiesel. And then a co-product that is also formed in this reaction is glycerol. And we actually decided to utilize this glycerol instead of just throwing it away and selling it as a co-product for additional revenue. And then finally, we move on to our final purification step, just to make sure that our fuel is as pure as possible so it can meet the requirements for it to be used in cars or whatever as our fuel source. So to do this, again, because the phosphates, as I mentioned earlier, were hydratable, we mixed our lipid stream with water to remove any residual impurities that were still left in our stream. And then we sent this mixture to a centrifuge to remove the water and also remove any residual soaps that could have been left. And so we're finally left with our ASTM-approved biodiesel. So now I'm going to pass it up to Dan to talk about our orange system, which is our co-product extraction.
Alright, so in order to make our system as profitable as possible, we use something called a biorefinery system. The biorefinery system means that we have to make use of all parts of the algae in order to make our system profitable. So to do this, we've created 3 co-products: eicosapentaenoic acid, or EPA, biomass, and glycerol. For EPA, it's an omega-5 fatty acid that's normally used in food supplements because it is very good for your health. We use EPA as our co-product because it is very abundant in nanochloropsis, and it is a very high value product that we can sell for $268 per kilogram. In addition, we can sell our biomass. You might not think that biomass can be a co-product, but it can be dried and sold as feedstocks for many other industries. And then, like Miranda said, we also produce glycerol from our transesterification reaction. Due to all the biodiesel production facilities, usually, or mostly the crop biodiesel production facilities, the glycerol market has been saturated, but the glycerol molecule can be converted to many other derivatives that can be sold at a higher price. So I'm going to talk about the EPA and biomass extraction subsystem, because Miranda already talked about the glycerol production. So first we have our biomass waste from the extraction system, and then that is sent to a filtration step right here, which then filters out the biomass waste, or the biomass which we can then sell as a feedstock. And then the stream that contains lipids and fatty acids is sent through a hexane extraction to extract these the lipids and fatty acids, which are then sent to urea crystallization. And urea crystallization is the main part of our EPA extraction process. In this step, the urea molecules crystallize and are able to entrap short chain-length fatty acids and leave the long chain-length fatty acids, such as EPA and a few other molecules, suspended in the solution. So this is important so that the urea crystals and the short chain-length fatty acids, which are in a solid form, can be filtered out, so just leaving the EPA and other long chain-length fatty acid molecules. And then this is further purified using another hexane extraction step, and finally we get a 70% pure EPA stream that can be sold at $268 per kilogram. So now that we've shown you our entire system, we can start analyzing it and comparing it to other models. So we've decided to compare it to a model by Lundquist. We decided to use this model because the model got their unit production cost of biodiesel down to $5.71 per gallon, which is pretty close to what our goal was. So first of all, we'll compare their design. For their model, they use a raised bed pond only. They don't use a photobioreactor at all, which can greatly reduce their costs, but it also can make their cultivation more inefficient. For their harvesting, they use bioflocculation or autoflocculation, which just means that they assume that the algae naturally flocculate and they don't have to add any flocculant to their system. So this can also greatly reduce their cost, both in energy and without having to buy the flocculant. They also use a drying step, but instead they just use solar drying, so they just lay the algae stream flat in a shallow pond and allow the sun to dry their algae, which is also very low energy intensive and low cost intensity. Then for extraction, they use hexane extraction. It's a SCCO2 extraction. But what is interesting about their extraction step is that they assume that they have, or that there's the hexane extraction facility is separate from their algae bioprocessing facility. So they assume that many different algae bioprocessing facilities share one extraction facility, which greatly reduces their costs because they don't have to pay for a portion of that extraction facility. Then finally, for additional revenue, they don't have any real co-products. They just consider revenue that they get from treating wastewater. So now comparing their production and their cost. Like I said, their unit production cost is $5.71 per gallon. So to make an equal comparison, we modified our system to have a unit production cost of $5.71 per gallon by modifying the throughput. So as you can see, we produce a little bit more diesel than they do, 2.78 million gallons per year. But our operating costs are much higher and our capital costs are much higher than theirs because we are able to have the revenue from EPA, which is able to offset the cost of producing the biodiesel. And then moving on to the life cycle analysis. The life cycle analysis is mainly use to evaluate how our system affects the environment. And the main two things that we are looking at are the water usage, the CO2 emissions, and the energy input and output. So for the water usage, you can see our system has a lower water usage than the Lundquist system, which is good because it means that we are using less water per amount of biodiesel produced. Also, we have more CO2 emissions, which is understandable because the CO2 emissions were calculated based on both the CO2 emissions from the system itself and also the CO2 emissions from combusting the biodiesel. And since we make more biodiesel, we would have inherently more CO2 emissions. For the energy output, we have less energy output than they do because the energy output is calculated by using the amount of biodiesel produced times around 36 megajoules per kilogram of biodiesel. So, but they also produce biomethane, which gives them more energy that they reuse in their system. So that's why they have more energy output. Now, looking at the net energy ratio, that's just the energy input over the energy output. And the energy input of our system comes from all the energy that's needed to run the unit operations and to heat and cool all of our systems. And for our model, our NER is about 5.1, which is very good compared to the current industrial model. But the future case of algae biodiesel production can even get down to 1.37 NER. So we could still improve our models. And now I'll pass it off to Selena to talk more about the analysis.
Thanks, Dan. So when we first designed the facility, it was outrageously expensive, and it was like $40 per gallon to just use any diesel at all. So our first profitable model that we did end up making, we had to take into economies of scale. So we just boosted up all of our flow rates until we got way out here. We were producing 30 million gallons of diesel per year to have a break-even cost, or a profitable cost. But this isn't very realistic if you want to have a startup, right? You can't have this ginormous facility and start off producing this much biodiesel. So we did this cost versus throughput analysis where we continued to decrease our costs until we had a break-even point right here, which is at 3.6 million gallons per year. So this is the minimum size of our facility that we have to make in order for our costs to be profitable. So within this 3.6 million gallons per year facility, our capital cost will end up being about $500,000, $561 million. Out of that, we have another $175 million of operating costs and a little bit higher revenue at $189 million. So out of that revenue, we can look at our four types of revenue sources. So we have our biodiesel, and then we have our three co-products. So glycerol, as you can see, produces very little, about $10,000 per year at our current size. And then we have biomass at about $3 million, and diesel at $17 million. And compared to all the rest of them, EPA far outseeds all these other three at $168 million of revenue per year. So then we went into a sensitivity analysis to see how much we could trust our data based on the assumptions that we made in our model. So for cultivation, we tested cell density. So to see how high we get our cell density, the more profits we'll make. We also tested our harvesting, the concentration that we can get down. The more concentration we can get ourselves, the smaller the volume that we're working with, and thus the cheaper it is to produce our oil. Extraction, we varied the pressure, and to see how that would affect our extraction efficiency. And then for transesterification, we tested the extent of the reaction going from our oil to our diesel. So this is what our graphs show us. So for this first one, we assumed 5 grams per liter in our model is what we can get for cell density. But if we can boost this up to 6 grams per liter, maybe through genetic engineering or better photobioreactors, we can actually improve our profits up to about $3. But then if it turns out that we were excited about how high we can get our cell densities, that would drop by another $2 of our profit. For extraction, for our formulation step, we saw the most variation in our prices. So we assumed that we could concentrate our cells down to about 20 grams per liter. But if we can actually get it higher, to like 30, we make almost $3 extra profit. And then if it's actually only $10 per 10 grams per liter of concentration, we'd actually see our profits fall almost $9 per gallon. For extraction, we found that as long as our pressure was above 30 megapascals, we had a pretty even amount of extraction efficiency. If it dropped below that, our profits dropped quite a bit. And then finally for transesterification, partly because transesterification, the diesel is not as high of a resource as our EPA is, we saw that this extent did not change very much. And this is also, we expect a high extent reaction, so it's not surprising. When we look into our subsystem costs, our cultivation is the most expensive one, followed by our EPA extraction. And then our harvesting and pre-treatment is the next biggest cost, and then finally our transesterification and oil extraction. So at the end of the year, we want to look back and see if we achieved what we set out to do. So we wanted to make biodiesel, and we wanted to comply to standards. So we did that. We wanted to test it, obviously, but we had enough purification steps that we reasonably expected to comply to standards. We wanted to have a really green process and incorporate recycling streams. So we did recycle. We recycled our flocculant, our methane, our methanol, our hexane, and our carbon dioxide. We wanted to extract co-products to offset costs, and we did. We found 3 co-products: glycerol, biomass, and EPA. And we wanted to use flue gas from industrial sources to kind of help make our process even more green, and we did. We cultivated in all of our steps with flue gas. And we wanted to produce actually about 250,000 gallons per year of diesel at least. And we did achieve that quite a bit. We actually are producing 3.6 million if it's going to be break-even price, which is also what it would have to be profitable. And then finally, 2 other things we were looking at were using wastewater as a source. So we actually contacted the Milwaukee Municipal Sewage District to get their sources for nutrient concentrations. And at least for Milwaukee, the nutrient concentrations are not high enough for our process to be profitable. We can't get a high enough cell density out of them. But maybe if we were to look into other wastewater sources, maybe agricultural or industrial sources, maybe a different city, those could be higher, and then we could use that to make our process greener, and then maybe get more profit because they pay us to treat their water. And then finally, moving forward, we probably want to make our process completely green and eliminate all of our organic solvents. So we do that quite a bit. We use a bioflocculant, we use carbon dioxide as an extraction fluid, but in our EPA system, we still are using our hexane and methanol. So maybe transitioning that into ionic fluids or another supercritical fluid extraction would complete making our process green. So future directions, I talked about a few of them. We'd also like to look into the effects of salt water on our equipment because we use a salt water from algae. We would also want to look into our wastewater additional sources and the profits that we can make from this. We would want to investigate additional sources, strains of algae, and maybe genetic engineering of them. And then ideally, if we were to make this into real life, we'd want to go through a lab and pilot scale tests, and then take into account marketing and transportation costs. So, in conclusion, we successfully modeled a biodiesel production facility. We found that we were very dependent on co-products for our revenue, and our break-even size, not counting capital costs, were 3.6 million gallons per year. And then finally, our energy efficiency is favorable compared to other models, but we still want to continue to decrease that value. So I'd like to acknowledge MSOE, the Department of Physics and Chemistry, and the Raider School of Business for their seed grant money. The Milwaukee Sewage Department for their numbers that Emily heard they gave to us for their concentrations of nutrients. Wesley Zoza for his graphic art that he produced for us for our literature review paper. Dimitri Pajides from Intelligence to report design for his counsel. And then finally, we have 2 advisors, our external advisor, Dr. Al-Hawagi, and then Dr. Devalina Gupta, who's also helping us with the review paper. Does anyone have